It is my biggest pleasure to introduce Professor Gordon Blair, Head of Environmental Digital Strategy at the UK Centre for Ecology and Hydrology, and Distinguished Professor of Distributed Systems at Lancaster. So yeah, I have known Gordon for like over 14 years. Before starting my PhD, it looks like, yeah, it's a long time. And we were working on an EU project, and I've learned a lot from him. So, and I was really pleased to see how he was able to align his expertise in distributed systems and also personal interest in environmental sciences. So his current research are how digital technologies such as the Internet of Things and cloud computing can help environmental scientists achieve a better understanding of the natural environments. And he has been working on it through different funding. So he holds a 5-year EPSLC Senior Fellowship in Digital Technology and Living with Environmental Change. And he's co-director of the Center of Excellence in Environmental Data Science. And he's also a member of the UKRI Digital Environment Expert Network. So looking forward to what he has to say about the, trustworthy autonomous systems and environmental science. So, Gordon?
Yeah.
All yours.
So thank you, Amel, for that very generous welcome. And it's great to see some old friends. And I look forward to this conversation very much. So let me try the share screen bit and keep fingers crossed that it works. Hold on a minute. I forgot to tick the critical box, didn't I? No, it's still ticked. Right. So it was fascinating getting this invite because, as I'll explain in a minute, my world has moved on somewhat, and I got this invite to talk about trustworthy autonomous systems. And I started to think, well, I don't really work in that area anymore. I used to, as I'll explain in a second, but what I do now is effectively environmental science. So I thought, well, can I really respond to this invite? And then I thought about it a little bit more. And what I realized is that exactly what I'm doing is working on trustworthy autonomous systems. So I'm going to take you on that journey. And it'll take a little while to get there, but by the end, hopefully we'll be in a position to have quite a rich dialogue about how trustworthy autonomous systems and the research that you're doing can help the world I'm now in, the world of environmental science, the world of responding to climate change. So that's the kind of where we're heading. So Amel's already said a little bit about this and explained my different roles, apart from my extra job as a part-time shepherd and a keeper of a flock of pedigree sheep. You forgot to mention that one, Amel, which is very timely at the moment because we're in the middle of lambing. So if I have to shoot off halfway through the seminar, you'll know why. But what you can see in this slide is a transition. There's a big transition from top to bottom. I'm a distinguished professor of distributed systems. I've worked on distributed systems and middleware for many, many years. I have quite a few contributions that could be called autonomous adaptive systems, having worked, for example, on reflective middleware, having worked on adaptive systems, having collaborated with people on models at runtime, which I see as a fundamental building block of autonomous systems. So I have that track record. But then as you look towards the bottom of my kind of CV, you see a big change. It's all about environment. It's all about environmental data science, right up until the biggest transition in my life, which happened in January this year, when I kind of left academia and took a role of head of environmental digital strategy at UKCEH, which is an organisation that looks at environmental science related to terrestrial and freshwater systems, effectively the land system in the UK and beyond. So a big change for me. I've maintained a 20% academic position, but I'm now largely applying my skills in real environmental challenges. So it's a big, big transition. So what led to this transition? I don't know if any of you have seen this movie. I go to the movies all the time. I love films. I always remember this one in particular. I don't know if you can remember what you were doing on the 21st of February, 2013.
Unfortunately not. No one is raising their hand.
Your memories are hopeless. I can remember exactly what I was doing on this day because I was going to the movies. The reason I can remember that day so well is because it was my birthday. And my wife said, I'm going to take you along to see this movie you really must see. And the movie was Chasing Ice. And it changed my life, to be honest. It's one of these moments that changes your life. Now, Chasing Ice is a documentary. It's a documentary that's made by James Baylog, who is an environmental scientist, who kind of got fed up with his science not having any impact and decided to turn to his other love, which is photography, to convey the message of what is happening to our planet. And he did that through the medium of ice, which he finds quite beautiful, awe-inspiring. So he made this documentary using his skills as a photographer to capture what's happening to ice around the world, in the Arctic and in the Antarctic and so on. And it's a phenomenal film. And I can remember sitting in that movie, with tears literally running down my cheek, because it was so moving, it was so powerful. And I always say that that's the moment when, for me, climate change went from being an intellectual thing, something of my head, to something of my heart. At that moment, I felt I had to do something about this. What can I do about it, though? I'm a computer scientist. I build middleware systems. What's that got to do with climate change? Well, 10 years on, there is a huge role for computer scientists and people working on autonomous systems in the environmental sciences. And I'll try and unfold that. Just before I do, though, I think it's maybe worth, since this moved me so much, just show a very short clip of Chasing Ice.
We're just observers, these two little dots on the side of the mountain. And we watched and recorded the largest witness calving event ever caught on tape.
So how big was this calving event that we just looked at? We'll resort to some illustrations again to give you a sense of scale. It's as if the entire lower tip of Manhattan broke off, except that the thickness, the height of it, is equivalent to buildings that are 2.5 or 3 times higher than they are. That's a magical, miraculous, horrible, scary thing. I don't know that anybody's really seen the miracle and horror of that. It took 100 years for it to retreat 8 miles from 1900 to 2000. From 2000 to 2010, it retreated 9 miles. So in 10 years, it retreated more than it had in the previous 100.
So that is why I'm effectively now working as an environmental scientist. That is a phenomenal movie, so I recommend it to you if you haven't seen it. There is a sequel as well, which is Chasing Coral, looking at the loss of coral reefs. So that began a journey for me into this world of environmental science. And it was greatly supported when I won a 5-year fellowship from EPSRC to study digital technology and environmental change. And one thing I realized very quickly is that environmental scientists need new tools because their world is changing dramatically. You know, they're being asked to answer very big, very pertinent, very important questions, and questions of real complexity. If you look back at environmental science maybe 15 years ago or 20 years ago, it was like any university discipline, it was really quite siloed. And you would probably spend most of your career studying one thing. It could be soils, it could be a particular behavior of soils, it could be the interaction of soils and worms, it would be really specific, and you would study that in great depth for all your career. There are environmental scientists still like that, but most of them are being asked to answer questions of, we have a changing climate, we have this river system, ecosystem, what do we need to do to manage that ecosystem, to manage the different pressures on the landscape? So they've gone from really specific siloed research to big, big questions, which require significant collaborations across disciplines. And also it requires an integration. And that integration is something I'll come back to, the drawing together of many different data sets of models. And that integration is actually what I've done all my career, integration, interoperability. So they need new tools, and technology can be at the heart of providing these new tools. In my fellowship, we worked through a number of areas actually where digital technology can have a very significant impact. And I've listed some of them here. This is not exhaustive, but there's certainly exciting new forms of data acquisition, which is leading to the point in time in which environmental scientists have an absolutely unprecedented amount of information at their disposal. That starts off with satellites, and satellites now coming on mainstream and providing open data to communities, whether it's to understand flooding or whether it's to understand drought or whatever, massive amount of satellite data. And then you have airplanes and drones providing image data as well at different scales. And then you look at the spread of sensors available, an Internet of Things of the natural environment, and ground truth sensors. And then you have citizen science, and then you have all the data you can collect from the web and mine from the web. Scientists are not short of data. And what we have is quite literally a sea of data. And if you want a mental picture, imagine environmental scientists drowning in this sea of data, unable to make sense of all the opportunities that they have at their disposal. On the good news, in terms of big data, we have so many innovations that came out of my old community in distributed systems, through cloud computing, through HPC facilities, through distributed computing. We have elastic resources in abundance to store and process that data. So the good news is we have a place to draw these data sources together, and we have the ability to run very large-scale computations on that data set and running them in parallel and so on. As well as cloud computing offering that collaborative environment, that place where scientists can come together and collaborate from different disciplinary traditions. And that drawing together of the hydrologist and the soil scientist and the chemist and the biologist is what is needed to answer some of these big questions, along with the data scientists and computer scientists, I should add. There's been an exciting world in terms of data analytics, and whether you call it data science or AI or some combination of both, there's a whole set of new techniques available to make sense of this data. So we have the ability to work this data and make sense of it and extract information and knowledge from the raw data. With just the caveat I'll return to in a bit, are the techniques fit for purpose for environmental data? And also, one thing I'm particularly keen on is there's also a whole raft of new ways of communicating, digitally inspired communication techniques. And as part of my fellowship, we work with artists and designers to design new ways of communication using, for example, Arduino, but being creative in how we get the message out there. In the same way that James Baylog was creative in how he communicated what was happening to our planet in a thoroughly meaningful way. So lots of new opportunities there for digital technology in this world. And perhaps you can see yourself somewhere in this slide thinking, you know, I've got that skill. You know, I could really help solve what I think is the issue of our time. So what I'm going to focus on, that's a big domain. What I'm going to focus on is something I've been working on in depth since I joined UKCH, and it's looking at digital twins. When I first heard this term, I thought, oh no, not another buzzword. You know, what does this mean? Are we going to overhype technology again? Is this just another buzzword? With just part of me saying, well, maybe there's something in this. And I now have come to the position thinking there actually is something in this. And I'll try and explain what that means, but only if you interpret the term correctly or in a certain way, it then becomes actually quite exciting. So as you probably know, digital twins are everywhere, and they emerged from the engineering domain. Looking at, for example, digital twins of an aircraft engine. And in some ways, I'm quite envious of that world because it feels bounded. I know it's not. I know it's complex, but compared to the natural environment, it feels bounded. And you can imagine how you would have a model that represents an aircraft engine, and then you can study the behavior of that aircraft engine through the model. I find this diagram quite helpful and to distinguish what a digital twin is. You know, many of us do models, and you know, having a digital representation of a physical system is not a digital twin, it's just a model. It's just a digital model. So we need to go further than that. There's lots of models that take input in terms of observation. You know, for example, there's lots of environmental models of hydrology to determine whether a flood is likely to happen in your home in the near future, or to predict how high flood defences should be in the far future. They often take data as input. Is that a digital twin? No. For me, a digital twin is when you have this two-way coupling between the physical and the virtual environment, and you have arrows in both directions. Now, effectively, what I'm going to do through a lot of the seminar is unpick these two directions. And what we'll start to see is a rather dynamic, rich, let's call it autonomous system emerge. So we're going to unpick the arrows as we go forwards, and we'll see a rather rich territory emerge. And it's with that rich territory that I start to get excited about what digital twins could mean. But just before we look at that, let's just turn to what it means to be a digital twin of the natural environment. I mean, the first thing to say is we're entering a world of massive complexity. People study complex systems, but there is no complex system more complex, if you like, than the natural environment, with all the interactions across all the different facets of the natural environment. So we're really dealing with grade A complexity. But I think there is a very compelling case to look at digital twins of the natural environment, partly because of that complexity and partly because of the urgency to be able to understand all these interactions in more detail and help manage our way through the crisis that the environment is in right now. You know, to look at mitigation and adaptation strategies that are well-founded. I think the first thing to say about this world, when you step into this world, is that you've got a slightly different perspective on what it means to model. And you have a massive, massive legacy of scientists who've built models of the natural environment, whether that's an Earth system model operating at the climate scale, or whether it's a hydrological model, modeling the behavior of a given river system with all its tributaries and all its hill slopes. There is a massive investment in process understanding and process models, and that exists. These are scientific mathematical models. They exist, they capture the best understanding of the science. They are a mathematical representation of the science in terms of equations. And that is what is at the beating heart of environmental science, that strong tradition of process understanding. In parallel with that, we have this unprecedented amount of environmental data emerging and the ability to extract knowledge or information from that data. So we kind of have two parallel pathways. We have a pathway of process scientific understanding, and we have a pathway of what we can learn from data. And for me, the grand challenge of digital twins of the natural environment is to marry the two, the process understanding and the data understanding, so that they can both learn from each other. Arrows again, interrelationships. And that's where it starts to get exciting. You know, because to be honest, most of the work of environmental science is being built on a tradition of process understanding with just a little bit of data assimilation to help steer the process models. But what I think we're talking about here is way richer than that. So perhaps this is a step change in modeling capability, both in terms of nowcasting, predicting the near future, and forecasting, predicting the far future. And I go back to this diagram, if you like. This is not just models. It's not just doing better models, more sophisticated models. It's not just digital shadows. We're going beyond that because we're interested in this two-way relationship. And also, when some people think about digital twins of the natural environment, they think of, well, let's build an Earth system model that understands the planet. It's not just about that glamorous end of the scale. It could be building a digital twin of how the river behaves in your catchment that runs near your house. So we're talking about digital twins across all the range of scales, not just the glamorous end, but the very meaningful end of how it affects where we live as individuals. So I wrote a short piece about this, which is actually in submission. It's not, hopefully it will be published, who knows? But I wrote down a series of challenges here. And these are the challenges I think we need to resolve to get there. You know, first of all, we need to achieve what I talked about earlier. So I'm not going to spend a lot of time about this. This harks back to my previous world, you know, to achieve integration, interoperability, and scalability. we kind of know how to do that. I think sometimes environmental sciences are not good enough at that, but we know how to achieve these properties. We know how to bring the data sets and the models together and allow them to talk to each other. And that is the middleware community that I came from. We know how to do this at scale. We know how to do this at ridiculous scale if we've got ambition to run these complex models many hundreds of times to really understand the uncertainties and sensitivities to different parameters. But then we move on, and then you get, I'm kind of using a jam sandwich metaphor here. Apologies to anybody that skipped lunch and is feeling hungry at this moment. But we then get the jam, the need to develop data science and AI techniques that actually deal with a messy world of environmental data, data that exists at different scales, data that's messy and incomplete because sensors break in the natural environment. Your data where you're as interested in the extremes and the extreme values as you are in the means and in modes of this study, because the extremes are where things are happening often. The development of data science techniques and AI techniques that are tailored for this world. And we've actually got a sister project called Disney between UKCH and Lancaster University that's doing just that. Achieving this process and data model integration, that's critical. That's almost definitional of what it means to me to be a digital twin of the natural environment and managing complexity, which I don't think we spend enough time thinking about. Really, what does it mean for a complex system with emergent behaviour? Now, that's why I'm really interested in talking to this community, because you do that. So, I'm just going to have a sip of tea, and then I'm going to step through in praise of arrows and unpick the interactions in a bit more detail. I'm like Billy Bragg, I can't perform without a cup of tea on stage, if you know the musician Billy Bragg. So here goes. So here I've got a very simple model, and it's going to become a lot more sophisticated over the next two slides, and it's then going to become something I think that's actually really quite interesting. So what are these arrows? What are these interactions, and where does computer science and autonomous systems help in building a digital twin? The first one's quite simple, but actually very important. You were getting data at such a volume now that basically the old ways of data ingestion can't keep up. So the first step is to get data into the system and quality assured and ingested and cleaned. And that cannot be a manual process anymore because of the volume of data. That's become a massive backlog in terms of environmental science generally. So we need to look at machine learning techniques, for example, and there's a whole body of literature out there that looks at determining anomalies, removing anomalies, deciding what to do, determining if an anomaly is an anomaly or is it an extreme event, because extreme events are really important and are happening with increased frequency. So the first important arrows here are sort of between data coming in and being cleaned and the interaction where data models or machine learning techniques can really help to automate or semi-automate this process. So that's a starting point, and that's quite a significant one. We move on and we get to what is often called data assimilation in the environmental sciences. And this is where you take the process model and you see some observations in the data world, and you think the process model is not aligned with observations. So let's nudge the model into a new state. Now, often these techniques are quite simple. They're used a lot in weather prediction, for example. And often the process models have to be set up to have some knowledge of state and to be nudged into new state. So it's quite rich, but it's also quite limited into what you can do. And that's often referred to, as I say, with the term data assimilation. I get quite cross. That's maybe not the right term because I'm quite an affable person, but I get quite irritated when I see people use the term data assimilation as the technique for digital twins, because what we're proposing actually goes way beyond data assimilation into a world of quite advanced interrelationship between data and process models, as I shall explain. We can do better than that, though, because as we apply AI or data science techniques to this massive data repository we have at our disposal, things will emerge. We'll see patterns. We can run different techniques. We can run change point detection algorithms, which is something we've been working on to determine, is there a fundamental change in a given signal or across a range of signals? Kind of multivariate change points. We can do extreme analyses. And all of these techniques are kind of determining higher order statistically significant events that have been observed in the data. There may be clusters, there may be possible correlations emerging, there may be things coming bottom up. This is rich information. This is rich semantic information about what's happening in the real world through observation. Are the process models actually aligned with the observations we're seeing? Not just in terms of assimilating a few values in, but in terms of what we're discovering about this data. And if not, why not? So we're looking at really challenging the process models. And here we can bring in the plural. It might not just be one process model. Often in environmental sciences, we run ensemble models, many models together. And what you can do is you can validate different models, or you can invalidate models, something that's quite controversial, because invalidating a model in this world is often invalidating a career. But not every model is able to represent different contexts in the same way. So what we're doing here is finding the right models for their given current context and challenging models and trying to improve. And then it starts to get really exciting, I think, from my previous world. You know, we can either adapt these process models as black box structures. You can tweak the parameters, for example. And by the way, some of these models are ridiculous in terms of parameter spaces. Some of them have hundreds of parameters. So don't think of your traditional function with 10 parameters or 6 parameters. Think hundreds, a massive space, and all these parameters are uncertain. But if that's the way it is, all you can do is tweak the parameters. But suppose this process model had an internal software architecture. Now, suppose it had a component which represented the particular physics of how soils will respond to moisture and what that means for release of carbon. Suppose there's an equation in there that represents that, and there's another equation that represents something else. And this is built up as a software architecture where you can dive in and find the parts of the system. So what you're doing is you're not looking at a black box system, you're looking at a very open architecture where you can then match the behavior of that complex system. You can self-organize yourself to represent what you're seeing in data observations. Now, this is starting to sound like quite a rich self-adaptive system. I'm hoping you can see that. I'm conveying it. And my good friend Keith Bevan, who's partly responsible for getting into this world as well, talks about this as modeling as a learning process. So modeling, you don't build a model, you build a process which learns over time and deals with changes as they occur. I'll expand on that in a second. I'm not finished yet. I've got more arrows to unpick. If you see in your fairly primitive, maybe data models you have, your extreme analyses, your change points, you see something emerging from the data pathway that's interesting, you can explore that in more depth. So you can create more complex data models, whether it's a deep learning system or an integrated statistical modeling technique or an emulator. You can dig deeper and you can build data models on top of the relatively primitive data models I've been talking about to explore given issues, to effectively build a more sophisticated data model of the parameter space. And you can dig deeper and see what the data is actually telling you. So that's my next step. If that uncovers something that you don't know, which is happening all the time in environmental science, a new behavior that you're detecting, which seems to be significant, you can maybe look at injecting new behaviors into the process models to represent that piece of physics that you think is emerging as really significant. So you can inject new behavior into your world of process models to represent that. You can also, one of the things that happens all the time in environmental science is that the process models are too big, they're too complex, they take too long to run. And that makes it really difficult to do either proper uncertainty analysis or build integrated models where you start to link these things together. They're just too heavyweight. So often you'll train from the process models, you'll build a data model, an emulator that represents the process model. And then you can train a data model from the outputs of the process model to mimic the process model in operation. And then that will run at a fraction of the time. So you can really work it and you can link it up with other models. So you can build emulators from the process model side back to the data model side. And also, if you determine there are uncertainties in your model, because one thing, if you're working in statistics, for example, or Bayesian statistics, you know the uncertainties and you know where they arise. You can use that then to build adaptive sampling strategies, which will say, there is great uncertainty. Can you go out and actually do some sampling at this point in this river? Because we really don't know what's happening there. And you can start to do adaptive sampling, targeted adaptive sampling based on the current state of the model. So what we have here now is actually adaptive modeling and adaptive sampling working together, a very rich adaptive scenario with many interactions across them. So here is my architecture for a digital twin. Now, here's where I see the role of data science and AI and autonomous systems in building digital twins of the natural environment. And what I've done here is just pull together all the arrows into one diagram. I'm kind of hoping that you're excited by this as a community, because to be honest, we don't have enough technical people working in environmental sciences. And when I talk now, I'm wanting to pull in more people because we need you. We need you to help build these kind of systems that I see as being providing the right tools for environmental science going forward. So this is an autonomous system. this is a digital twin of the natural environment. The two, for me, have merged and become synonymous in my head. And this, to build something like this is a grand challenge, not least of all because of the legacy we have in environmental science of many of these models being constructed and rather old software engineering practices, often written in Fortran, to be honest. So this isn't your contemporary world of agile computing and Python and data science libraries. This is a very different world. So that's kind of where I wanted to get to. So I'm just kind of summing up a little bit now. But I just wanted to, before I do that and then turn to questions, I just wanted to point to two ongoing projects that we're working on, both of which have deadlines this week. So if I look stressed, that's why. And the first one is a NERC-supported project to look at information management framework for digital twins of the natural environment, to look at how you do effectively the integration, interoperability, and scalability, the bread and butter challenges. So we're currently working as a consortium across all the NERC science centres to build an architecture for this information management framework, which has at the middle of it an asset commons to bring together and integrate all these important assets, data, process models, data models, workflows, and so on, and to use semantic constructs to describe these things and be able to discover them, and then to reason about interoperability. Going back to the previous project that we worked on, Amel, in terms of being able to dynamically connect things and allow them to interoperate. So that's one project that I'm working on at the moment. And another one we're working on, CEH has their own particular challenge they're working on in terms of building a digital twin of the natural environment. And we have a short amount of funding to try and rapid prototype this. And we're hoping for further funding to take it further. And this is a digital twin of the land surface, an area that UKCH majors in, and we'll have a lot of data coming from very sophisticated sensor networks. For example, the Cosmos soil moisture network up and down the country. So there's lots of insights coming from data, and there's also significant investment in a process model called Joules, about to be hydrojoules, but having work of the two worlds of hydrology and soil science kind of mashed together. So we're currently looking at building a digital twin in the cloud environment for this very important area of how the land surface operates. How effectively is it in growing food under different climate conditions? What's the importance of soil moisture in that process? Is there a risk of the soils leaching carbon? And important questions like that. So that's kind of a mention of two projects we're working on. And since you do trustworthy, I haven't majored on trustworthiness, particularly in this talk. But I just wanted to mention that I work with a fantastic cluster of PhD students who are mainly social scientists and who help me reason about how to do this in a way that's important for society. And I'll just highlight the work of Lauren Thornton, who works with me, who's looking at how to make these systems trustworthy by design, which is her PhD topic, how to make reasoning about environmental systems and environmental data trustworthy by design, and looking at issues of openness and transparency, for example. So that I just wanted to throw out, although I haven't majored on trustworthy in this talk, I've majored more on the process side of things and autonomous system side. This is enormously important, and making these systems trustworthy, particularly when you're making big decisions about climate change and you're right at the heart of public and government debate, trustworthiness is crucial. So I said I wanted to leave time for questions, and I think I've kept my promise. Just to sum up, this world I'm in has never been more important. That goes without saying. And the world we're in is changing very rapidly and really needs massive cross-disciplinary, I call it transdisciplinary effort to respond to the challenges ahead. That includes computer scientists and data scientists. Pretty please. I've convinced myself through this journey, which I've kind of documented in this talk, that digital twins actually do mean something. It's not a hype. If you interpret it in the way I've talked about it, as bringing together insights from data and process understanding and looking at the two-way relationship, then that is exciting. That is a step change. That's a potential paradigm shift in improving our modeling capability. I'll go back to the phrase of Keith Bevan, modeling is a learning process. Models that improve over time and can learn from observation, and actually the two worlds can learn from each other. Now, that is a very worthy goal, and that, for me, makes digital twins of the natural environment a really exciting place to be, and hopefully also an exciting place to be for the autonomous systems community. And I'm done. I have a series, I'm happy to share my slides. I've got a series of musings there that I've drawn on for this talk. And with that, I'm happy to take questions, and thank you for listening.
Thank you, Gordon. I have Bashar is waiting for a question, so I'll hand over to Bashar first. Thank you, Gordon. Yeah. Go ahead.
Thank you very much, Gordon. That was really inspiring and really very nicely framed. So I really appreciate that. Lots of stuff to think about. I don't know if I'd be asking an orthogonal question here, but I suppose one thing that crossed my mind as an engineer is what the role of engineering is. I understood it from what you've described as I guess, you know, supporting the data scientists, supporting the environmental scientists by providing better engineering of the tools that you described, which is fantastic. Of course, I think that's a really good goal. But I'm also wondering whether perhaps we're missing a trick here in the sense that we can also contribute to the solution and not just to its understanding.
Yeah.
To understand the solution and not just understanding of the problem. And to do that, we need to be able to represent potential processes for intervening. So we need to understand about control and understand how we introduce instruments in the world that might actually perhaps play around with phenomena in the world, both captured as data, but also in the actual world itself, perhaps through machinery or through modification of human behavior, through socio-technical systems and so on. So I'm trying to drift towards a question here, which is, where is the role in your big picture for this? Because as far as I could tell, your digital twin, or your model of what a digital twin could do was rather, and this is not in a bad sense, it was rather passive and not in the way that it might, for example, be used in, say, manufacturing, where the digital twin actually intervenes with a physical process to produce something. So I'm just wondering if you had any thoughts on that sort of possible role of intervention by computer scientists and not just provision of understanding.
Yeah, I agree with exactly where you're coming from, by the way. And first thing I'd want to say is that computer scientists are not just here to help support the engineering. They're a fundamental part of the solution space. One thing I'm passionate about is cross-disciplinary solution spaces and how to make that work effectively. And I'm actually, in the work I'm doing now, I'm being challenged more as a researcher than I ever was doing pure research, because I'm being asked really potent, powerful research questions about my computer science and about software engineering and about how that interacts to do innovation. around environmental science. And often what I bring can lead to innovative solutions just as much as the chemist can. So it's that meeting point of all the skill sets, and it's an innovative process. I might have misrepresented, probably because I had limited time, what I was talking about with digital twins, but absolutely interventions are important. Yeah,
I suppose my one thing that concerned me, or sometimes concerns me, is that of course the natural world also contains human beings and machines that human beings build, and they have almost become part of our natural world, not to the extent that they follow the laws of nature, but they follow sometimes some of the laws of physics and some social laws and norms and behaviors that we need to somehow capture. And I'm wondering how we can capture that.
No, very important. Again, I actually said to Amel before we started, if I don't manage to mention the role of humans in the loop, make sure I do so. So you've just opened the door, because I think we're even more important here. You've got scientists in the loop, and scientists have got all this experience. This is not an autonomous system. It's a semi-autonomous system with humans in the loop and scientists helping to work alongside machine. In terms of understanding insights, are the insights valid? What does this mean? So when you look at all these arrows, these are not automated arrows, they're semi-automated arrows. And all over that diagram, there's humans and the need for socio-technical understanding, which is why I'm so passionate about working with my little cluster of social scientists on these issues.
I promise not just the tiniest of follow-ups, which is, it's not just humans in the loop, but also airplanes in the loop, or cars in the loop, or physical devices that we have in the loop that we also need to somehow capture in the discourse.
This is both the magic and challenge of environmental science. You've got to look at interactions between all these elements. And some of the more advanced environmental science is building models of society and different sectors and how that interacts with the science. That's very difficult. I'll let someone else come in.
I think Ushnish want to ask another question related to people. Go ahead, Ushnish.
Yes, thank you. So just if you don't mind, maybe expanding on your thoughts on trustworthiness. So there's one aspect is, of course, changing the minds of climate skeptics, but the other aspect I'm seeing more and more of is equity-seeking communities saying, hey, these solutions are not going to work for us, or not going to solve the problems that are relevant to us. It's only going to solve the problems or benefit few people. So if you don't mind maybe expanding on your notions of trustworthiness.
Yeah, I probably don't have too much time to go into that, but I will push you towards Lauren Thornton's paper that's cited at the end. It's the only time I've managed to have a paper with a title 50 Shades of Grey. That's a masterful title. And what that looks at is it looks at exactly this issue, because trustworthy, I think environmental scientists have really been rocked by a lack of trust in science. And we need to make sure when we build these systems, we build trust in. And that's a huge, complex socio-technical issue for how to derive this trust. So what Lauren's been looking at is the various potential elements of trust around openness, for example, around transparency of the scientific process, to see to what extent you can fold in these different elements to build more trustworthy systems. Now, our PhD is much more richer than that, but that's a kind of short version. And I really enjoyed that paper. I mean, I'm a co-author, but it's really Lauren's work. It's a really nice paper, that paper on 50 Shades of Grey. So I recommend you read 50 Shades of Grey. Just make sure you get the right version.
Okay, thank you. Gordon has to leave, but Colin, if you want to ask a very...
I'll take one more, because this is interesting.
Okay.
Thank you very much, Gordon. Thank you for your time. It's fascinating stuff. One thing you said really resonated with me, and I'd like a little bit more information, is the invalidation of models. I think this is absolutely right and absolutely and a challenge to any engineer to say throw away and start again. Do you have advice on how that can be done? You know, the scope in which this is, you know, some of the tools that people might use to justify that really big change?
It's actually not a technical challenge, it's a cultural challenge.
Yeah.
And I mean, this is again one of Keith Bevan's thing. What Keith Bevan is looking at is not a model that will tell you the answer if you run the model all over the country 100 times, because the answers have got to be tailored much more to the given situation, the given context, the place, maybe even the hyperlocal place. And to do that, you've got to be prepared to say that models won't get everything right. It might be right to represent the Southeast because it captures the physics there quite nicely, but it doesn't work for the peatlands or for it. So if you put it in that way, it's slightly easier because it's easier for a modeler to admit that my model's not perfect for everything, rather to say, oh, your model's rubbish. So if you frame it as a way of finding the right model for the right local context, and you're finding the right mix of models that represent the physics of that particular context, I think that helps enormously.
I totally agree. What brought to mind when you were mentioning that was the current the situation we had with COVID and the models we had coming out of Imperial, where people were saying they're models for a reason. But so often people expect a model to be perfect everywhere.
Yeah.
And I wonder, you're right, and whether it's a human thing, and we just have to be much clearer in stating purpose for models.
Yeah. Environmental scientists are quite modest about their models. They're building such complex systems that they know the models are imperfect. But then again, careers are built out of models. You know, and CVs are built around models. So that makes it slightly more difficult.
Great, thank you.
Yeah, good question.
So thank you. There are actually more questions coming up, but Gordon, I know that you have to leave, but I'm sure they can reach out for you.
Oh yeah, please do reach out. Send me the questions, or if you can capture the chat, I'll happily respond offline.
So thank you, Elias. If you can type it, I'll transmit it to Gordon. Thank you very much, Gordon. Thanks again for the great talk and the inspiring talk, as Bashar said. Thank you.
Yeah, and nice to see some old friends.
Thanks. Thank you, Gordon.
Right. Okay. Bye.